So in addition to addition polymers, which we saw previously and had to do with alkenes linking up, monomer units that are alkenes linking up and forming long chains of repeating units, there are also polymers known as condensation polymers. So condensation polymers form through condensation reactions. And a condensation reaction is one in which two smaller molecules are linked together, and in the process, water or some other small molecule is released as a byproduct. So this is known as a condensation reaction. Another possible byproduct would be HCl, but for the most part, the byproduct that they'll show you is water, H2O. So some examples here, you can see this molecule on the left is one monomer, or in this case, we have the same monomer on the left and on the right. So there's an OH here and there's an H here. And so the OH and the H are going to link together and leave as a water molecule. And in the process, that formed a bond between the two monomer units, which is a covalent bond. And so that's how these units will be linked together. There's two different kinds of condensation polymers that you need to know. One involves the formation of ester groups between the monomer links. So it's a condensation reaction to produce an ester. And the other one is a condensation reaction to produce an amide. And so we're going to have two different kinds of condensation polymers called polyesters and polyamides. To form an ester, you need to have, or usually need to have, carboxyl groups and alcohol groups. And so you can see that we have OHs on both of them, but essentially all that matters is that we're going to remove an OH from one and an H from the other. And so that will produce the water molecule as the byproduct. And in the process, we're going to link together the C to O double bond. We do a different color. The C to O double bond and the oxygen single bond, and that will lead to the ester group, which as we know is the Koch group, the COOC. So carboxyl groups and hydroxyl groups, or carboxylic acids and alcohols, can condense together to form esters. On the other hand, carboxylic acids and amines have a primary amine anyway, would look like this with an NH2. So if we say this is R1 and this is R2, well, again, we have H and we have OH. So that part can leave as a byproduct and we'll get water. And then we would pull the other two groups together. So there's the double bond and there's the NH. And so now we'd have an amide group. So that C to O double bond connected directly to a nitrogen. This group here is known as an amido group, or making the molecule an amide. So both of these reactions involve the pulling together of smaller units and the removal collectively of water molecules from between those two units, and that bonds them together. Okay, so how does this lead to polymers? Well, the only way that this can lead to polymers is if the monomer units have two of these functional groups on either end. So they have one functional group on either end. So one example here where these boxes, this is taken from the Pearson textbook, these boxes are just meant to be kind of like R groups. It could be anything in between the functional groups. But this is an example here of a dicarboxyl or a dicarboxylic acid. So one monomer has two carboxylic acid groups, and this molecule here has two alcohol groups. So we'd call this a diol. So we have a dioic acid. Maybe I'll rewrite that. We've got a dioic acid, and we've got a diol. So you'll notice that that's a little bit different than the addition polymers. So in condensation polymers, you can have one monomer or you can have two different monomers. So in this case, we actually have two different monomer units. We have the yellow monomer unit on the left, and we have the second monomer unit on the right. When they bond together, we're going to be removing that water molecule that's over here and creating this ester link. But now you can see the reason why these can continue to react and form long chains is that because they had two functional groups on their ends, now there's remaining an acid group on one end and an alcohol group on the other end. So those groups can engage in additional condensation reactions. So eventually you can form long chains this way. So a specific example is shown below. You have a monomer on the left and a monomer on the right in green. They are going to remove this water molecule as the byproduct. And so we've now made an ester link. Now, when you draw polymers, just like with the addition polymer, you're never going to draw the whole polymer because it's a huge molecule, thousands, potentially thousands of units long. And so you're meant to know how to draw the repeating unit. And so the key thing about drawing a repeating unit is that you show parentheses or brackets on the ends. You write N on the outside to imply that this can repeat any number of times. And you draw the bonds extending through the brackets. This implies that this is just one unit and that it continues on either side. So notice that at the ends, we've kind of removed that water molecule from the end. So if you look up above where this was presented, right? So this was the unit after one condensation, but when the repeating unit is drawn, the H and the OH, so what would happen next when they link up, that has been removed when we go down here to the repeating unit. So you have to be able to show what happens when the two monomers link together. So that's this process. You've shown the ester link here forming, and the water is the byproduct. And then if you're asked to draw a repeating unit, you should be able to remove an additional water molecule. So we're removing a little bit from each end, the H from this end and the OH from this end, and we're showing these bonds extending through the brackets to imply that this thing is just one unit and it's part of a longer chain. Okay, if we go on to polyamides, it's essentially the exact same idea, except now the groups are slightly different. We're going to have carboxylic acid on one side and amino groups on the other side. When we remove the water molecule, we end up with this amide as the functional group in the middle. So with a specific example, you can take away the H2O again. There's your byproduct. Here is your amide link. And so now we've linked together these two molecules. If we want to show the repeating unit, which is moving down here, then we have to remove an additional water from the two side groups to show that this is going to continue on. So we've taken away an H from the nitrogen, and we've taken away minus an OH from the carboxyl group. So that is always what's going to happen. We're always going to take an OH away from the carboxyl group. That's what happened up here, right? And we take away an H from the alcohol group. Down here, once again, we take away an OH from the carboxyl group, and we take away an H from the amino group, and then we can draw the repeating unit. And so that's how we get these condensation polymers. Now, it's also possible if you had just one monomer. So let's say it was just R, and on one side you had a carboxyl group, and then on the other side you had an amino group, let's say, or you had an alcohol group. So this is actually what an amino acid is. It's an R group that has an amino on one side and a carboxylic acid on the other side, so that's why it's called an amino acid. And so here you don't actually need two different monomers if you have something that's both an amino and a carboxylic acid, because you have an H and you have an OH. So these units can now link together all by themselves. And so you could essentially have a repeating unit of just this one amino acid. And so the repeating unit would just be shown like this, where I've removed the water collectively from either side, and I'm saying this thing could repeat. Or in the case of real proteins, the R group varies. So the R group can be R1 or R2 or R3. You keep changing the middle part of the amino acid, and then you can get essentially infinite complexity by making chains of different amino acids. But the actual bonding, the actual chemistry is all the same. We're just doing condensation reactions to link together these molecules. So for condensation polymers, we can make polyesters if our monomers have acid and alcohol groups on their ends. For polyamides, we need carboxyl and amino groups on each end. You can have just one monomer that has one of each of these groups on its ends, or you can have two monomers in condensation polymers that have two of the same, like two acids, and then two amino groups on their ends. You should be able to draw repeating units, as we've done here, or you should be able to undo a repeating unit. If you're given the repeating unit, like this one, we should be able to work backwards and know which bond to split. So if I was looking at this, I should realize that that's an amide link, and I should be able to cut that bond apart, and I should add back an H to that nitrogen, and I should add back an OH to that carbon, and then I should be able to just essentially copy the structures, and I would also be adding an H back to this amino on the end, and I would be adding an OH back to this one on the end. So if you wanted to draw the two units, you should be able to undo a repeating unit to draw the monomers that formed a particular polymer. The final note is not, essentially what I just did above is I did a hydrolysis reaction. So the opposite of a condensation is a hydrolysis reaction. So they both have to do with water. And if you break down the word hydrolysis, it means cutting with water. Usually there's some sort of enzyme or acid involved to make this hydrolysis process happen. The water on its own would generally not cause this reaction to happen very quickly, but they call it hydrolysis anyways because the net reaction involves the adding back of a water molecule and the cutting apart of the covalent bonds. And so that's what I did up above. When we break apart an amide group, we separate the monomers apart, we end up adding back H and OH. And so we've cut the bond apart and then we've added back water, and that's why it's called hydrolysis. I add back the H on this end and I add back the OH on this end to show the breaking off of the extended bonds. And again, I'm adding back water. So hydrolysis is the name of the reaction. We add back H2O and we cut a covalent, we break a covalent bond. So that's how we break apart these condensation bonds or these condensation polymers, whereas condensation is the linking type of bond, type of reaction.